Alright, so let's introduce even more definitions before actually getting into some actual math. So, a ring homomorphism is a map from a ring R1 to a ring R2 such that, so basically it needs to be a group homomorphism under addition and a monoid homomorphism under multiplication. So, for the group homomorphism, all you need is that if you take two elements A and B in the ring, then f of A plus B is f of A plus f of B. Remember, this addition takes place in R1, this addition takes place in R2. And the other thing, so for multiplication, it's a similar thing. F of A times B equals f of A times f of B. Here, this multiplication takes place in R1, and this multiplication takes place in R2. However, we have this other thing of f of 1 equals 1. Of course, here this is the element 1 contained in R1. This is the element 1 contained in R2. If you have two different rings, then they could have different, their multiplicative identity elements could look different. So this sends the multiplicative identity of R1 to the multiplicative identity of R2. And let's see here. So it is sort of interesting that here, if you know that f of A plus B equals f of A plus f of B, then you can conclude that f of 0 is going to equal 0. So the reason that is because if you take f of 0, that's f of 0 plus 0, which is f of 0 plus f of 0. So here, let me write it out. You have f of 0 equals, well, 0 equals 0 plus 0, and since this is a group homomorphism, f of 0 plus 0 is equal to, you take f of 0 and you add f of 0. And so then from here, what you do is you subtract, you subtract f of 0 from both sides of this equation, and you end up with 0 equals f of 0. And so that's how you get f of 0 equals 0. However, that step that we did at the end there, subtracting f of 0, that's cancellation. And the reason we're able to do that is because we know that f of 0, no matter what it is in the ring, it will have a additive inverse because this is a group. And that step does not work in a monoid. And in fact, you cannot conclude from this equation, just because this equation holds, you are not guaranteed that f of 1 is 1. And so therefore, you need to add it in as an additional requirement for your definition. So anyways, let's look at an example. We sort of typically, well, we know quotients, and typically those are related to homomorphisms. So if you take an ideal A, then we have a projection homomorphism, which you send an element R to the coset R plus A. Another example, for any ring R, we get this is sort of interesting. I think this is sometimes called like the prime ring of, like if you're given a ring R, then this is like the prime ring of R. I think Jacobson calls it that. I haven't read it in a while, I forget. But so anyways, what we do is we take an integer m and we map it to the multiplicative identity of R added to itself m times. So we will take 2 to 1 plus 1. We'll take 3 to 1 plus 1 plus 1. And we will take 0 to, well, we'll take 1, that will just go to 1. We will take 0 to, well, 0 is just adding something to itself like no times at all. And so we're sort of multiplying by m in here, and multiplication is just adding something to itself. And so in that convention, the way we do it with numbers is that, well, with integers, is that you take something times 0, that's just not doing anything, so it's 0. So this will map 0 to 0, and if you take a negative number, then you're just negative 1 will get sent to the additive inverse of the multiplicative identity, which we will typically just refer to as negative 1 or negative 1r if we want to specify r. And then, so like this will map negative 3 to minus 1 or negative 1 minus 1 minus 1. So that's another homomorphism that we get. All right, so let's prove a thing. So if we have a ring homomorphism from a ring R1 to R2, then the kernel is an ideal. And this I alluded to earlier, that ideals sort of ideals in ring theory play the role that normal subgroups played in group theory. All right, so let's prove this. The first thing you need to be an ideal is it needs to be an additive subgroup, meaning that it needs to be closed under addition and contains 0. But that's sort of obvious if you take... the reason it's obvious that this is a subgroup is that if you take like f of r plus s, it's going to be f of r plus f of s. And so if r and s are in the kernel, then if r and s are in the kernel, then f of r equals f of s equals 0. So this is going to equal 0. So f of r plus s equals 0, and therefore r plus s is in here. And so therefore this is closed under addition, and certainly f of 0 is 0 because it's a homomorphism, and so we're good. Right, I even said that there. I didn't even, well, having this, I didn't even need to say this part. What I do need to say, though, which I didn't say, I think this is what I meant to say, is that, well, no, you don't need... Yeah, we have 0 in there already, and there's no, we don't really need this, right, because ideals don't need to have 1 in them. Let me see what we... Yeah, because if you have 1 in there... Right, you need to have 1 in a subring, but you do not need to have 1 in an ideal. And in fact, if you have 1 in an ideal, then you have the whole ideal. Because ideals are closed under multiplication, and if you take 1 and multiply it by anything, you get that thing. And so you get the whole ring. So that's also a really important point. But anyways, so we're in the middle of this proof. So if we take any r and a in the kernel, then far is we just use that it's a multiplicative homomorphism. It's f of a times f of r. Well, since a is in the kernel, f of a is 0, so we're taking 0 times f of r, and so that's 0. And similarly, we get f of ra is f of r times f of a, which is going to be f of r times 0, which is 0. All right? And it is important to notice that we're using this fact that anything times 0 equals 0, and that's true, but you don't get it automatically. You have to prove it when you're first starting out with rings. So let's go ahead and prove it. It's pretty straightforward because you just take 0 times a is 0 plus 0 times a, and then you distribute. So we use distributivity here. It's not like, so we actually have to use stuff, I guess. So anyways, from here, now because this is a group under addition, we can cancel out a 0 times a on both sides, and we'll get 0 times a equals 0. And then you do the same thing, but you put the a on the other side, and you use the other distributive law, and you get that a times 0 equals 0. Ow. All right. So for an example, so ideals of the integers. We know just from basic group theory, you proved that the subgroups of the integers are just of this form. We'll write it as in a particular integer in parentheses, and that's just all. So here, this will be m. So all ideals, all subgroups of 0 are of this form where you take some element m in Z, some integer m, and then consider all integer multiples of that particular integer. So those are all the subgroups, and you can see that this is going to also be, if you take anything and multiply, if you take any element in here and you multiply it by any other integer, then you're also going to get an integer times m, and so it's also going to be in here, and so it's going to be, and so this not only is a subgroup under addition, but it's closed under multiplication. Closed under multiplication by any other integer on the left or the right, and therefore this is an ideal. All right, and certainly it contains, do we have to have 0? Well, right, it's a subgroup, so it contains 0. All right, so let's do another proposition. If we have a ring homomorphism F from R1 to R2, and we, basically what this is saying is that if you have a homomorphism, you can pull back ideals and push forward subrings. You can't, in general, you can't do anything more than that, but if you have an ideal in R2, then the inverse image under this homomorphism is an ideal. And if you have a subring here, then its image is a subring. So to prove this, first of all, you need that F inverse of A is a subgroup. So here we're proving that the pullback of an ideal is an ideal. So this thing is a subgroup because if you take any element, any two elements A and B in A, and so since these are in A, right. So what we're doing is we're starting with, what we're really starting with is, because we want this to be a subgroup, we want to start with elements A prime and B prime. And A prime and B prime are in F inverse A. And the fact that they're in F inverse A means that there are things in R1. No, to say that A prime and B prime are in F inverse A means that the images of A prime and B prime under F are elements of this ideal A in R2. So therefore there are elements A and B such that F of A prime is A and F of B prime is B. So given all this, then if you take the sum of these two things and you map it under F, well, you just use that as a homomorphism, you get these two things, but this is A, this is B, and this is just the sum of two things in an ideal, and so this is in the ideal. And so F of A prime plus B prime is in this ideal, which means that A prime plus B prime is in F inverse of A. And certainly F of 0 is going to be 0 because it's a ring homomorphism, and so this will also contain 0. All right, so that's that. And then the other thing, so for multiplication, if you take an element R in R1, then fra is going to be F of R times F of A, which this is, we're just taking some element of R2 and multiplying it by F of A. No. A prime is in R1, so F of R times A prime will be F of R times, and then the image F of R times F of A, but this F of A, this is A prime. No. This is F of A prime, which is also A. That's a horrible thingy, but I'll keep it. Anyways, so F of R times A, well, A is an element in an ideal, and this is just some element of R2, and so multiplying it will leave us an A. And so therefore, since F of R times A prime is an A, we know that R times A prime is in F inverse of A. And similarly, the same argument on the other side, F of A prime times R is going to be an A as well. And so that makes it an ideal. And to prove that the image of A is a subring, you basically just use homomorphismness. So F of A times F of B, if you multiply two things in the image, then you can bring them inside because it's a homomorphism. And let's see here. So if here A and B are just two elements of our subring A, and so then the product is also in the subring A. So this is an A. So f of A times B is in the image of A. And so it's closed under multiplication. Similarly, it's closed under addition. All right, so now what about other, like, can we do more than this? Like, can we push forward an ideal? And it turns out, no, you cannot push forward an ideal, because here's an example. You map the integers into polynomials with integer coefficients by inclusion. So you'll map the element 2 to the polynomial that's just 2 times x to the power of 0 and nothing else, because x to the power of 0 is 1. All right, so we know that this is a homomorphism. Well, you can check that. It's just inclusion, so it's obviously going to be nice, so long as these two things are nice, which they are. And we know that, let's take an ideal of this form, n, so all integer multiples of a particular integer n. Then it turns out that the image of this is not an ideal because, for example, because you would need to be able to multiply any polynomial by this, you need to be able to multiply any polynomial by any element in here and stay in here. But that doesn't work. You just take the polynomial, just x by itself, and you multiply it by n, and that certainly can't be in here because x is just some symbol, and it's not going to be an integer multiple of n. But because f is inclusion, this is just, like the integer multiples of n it's basically the same thing. So x times n is not going to be in here. So this thing is not closed under multiplication by all elements of the ring on the left. And so it's not a left ideal. And it turns out it's not a right ideal either because you just multiply the x on the other side. And therefore it's not an ideal. So yeah, this is a bunch of stuff about rings. And now we're going to talk about ring homomorphisms and in particular isomorphisms.